Okay, so yeah, let's go. So hi everyone, good afternoon. So I'm Pierre. I'm a lecturer at the university here. I want to talk about some very basic notions of system software security. So I'm an operating system person. So by system software, we mean all this low-level software that kind of manipulates the hardware directly. So obviously operating systems, but also hypervisors. So that's why I will talk about both operating systems and virtualization and other types of system software, things like web servers, standard libraries, interpreters, and things like that. So this is also system software. So everything that I'm going to say will apply to operating system and hypervisors, virtualization. But there is also a lot of general things about system software in general. So I'm an OS guy, and I used to, when I did my PhD, I was working on performance, like how can we get as fast as possible? It was the main thing. Okay, power consumption was important too. And these days, since maybe 3 or 4 years, I realize that I'm almost entirely doing security, because this has become like a fundamental topic in system software. And I will try to motivate a bit about this thing in this talk. It has always been something super important, but today more than ever, you have at least 1 or 2 security track in every system software flagship conference. And you have at least 1 kernel memory safety track on the big security conferences. So it's something super important. And then if you want to get funding for your research, it turns out that today is actually quite a good time if you are doing cybersecurity. So that's also one thing that drives your research, right? The money that people will give you according to which field you work on. So I got in touch with the organizer from Crashester, and thank you so much for letting me do this presentation today. So I want to talk about the basic principles of system software security and memory safety. For some of you, this may be something you already know, right? So I do apologize in advance. I also apologize if it looks a little bit like a lecture, because this is what I'm used to do, but I want this to be as interactive as possible. So please, if you have a question at any time, interrupt me, raise your hand. If we can have an exchange, it's even better. So don't hesitate to interrupt me. And hopefully, you'll learn some stuff. So yeah, let's get started. Okay, so I speak about some general notion of security, and I will really insist on the notion of isolation. So that's one of the fundamental principles of operating system / virtualization security. Actually, operating system security covers so many things. I don't have time to cover everything. We are talking about user management, file permission, things like that. So I would really focus on the notion of isolation, and especially the isolation of memory, which is, it's a research field in itself. Then we'll talk about what are the different types of attacks that we can, that exist to break this isolation in the domain of memory safety. So that will be something that applies to every possible system software. So we'll look at memory vulnerabilities that you will commonly find in memory unsafe languages like C and C++. So all the system softwares are written in these memory unsafe languages. And we'll see how some seemingly benign bugs that have been introduced by a programmer, like just a programming mistake, they can lead to some pretty serious security issues. I'll talk a little bit about the defenses that have been implemented over the year. Security is always an arms race, right? Someone invents a new attack, everybody's freaking out, someone comes with a mitigation, everybody is like, phew, and then someone comes with a new attack, so, system software is no different. There have been attacks more or less advanced and corresponding defenses being developed throughout the years. And then a brief conclusion. So let's get started. Let me check the time. Okay. So let's have a look at some general notions. So this is the kind of picture that I put in all my slides regarding operating system. I'm sure you have seen pictures similar to this. the operating system manages the hardware directly. Okay, and you have the applications running on top of the operating system. So say you want to run a web server, Apache, you're going to run a Linux kernel on top of your physical machine, on top of your hardware, and then Apache is going to run on top of the operating system. Now, Apache wants to access the network card, it wants to access the memory, it wants to run on the CPU. And it's a bad idea to let an application, Apache, access the hardware directly, right? You don't want to do that, because if you give too much power to an application, maybe it's going to crash the system. Maybe it's going to look at the memory of another application, and you don't want that, right? Say you have Chrome, the web browser, something that is very prone to being hacked, right? Who knows which kind of website you are using with Chrome? This is something that is really prone to get hacked. And then you have your password manager on the side, like it's another process, right? You don't want Chrome to be able to look in the memory of your password manager, because you know that your password manager is pretty secure in itself, right? It's not connected through the network, it's connected to nothing. It's probably not going to get hacked, but you have another piece of software, Chrome, that is very vulnerable. And assuming an attacker can easily take over Chrome and then look at the memory of your password manager, well, you're screwed, right? So this will come back to isolation. But long story short, you don't want to let an application access the hardware however it wants, right? It needs to go through the operating system that is arbitrating every access to the hardware, right? You don't want an application to erase your entire hard disk. It needs to be arbitrated by the operating system. And this is true for all the hardware resources, CPU cycles, CPU cores, the main memory, secondary storage, your disk, your SSD, the network card, and so on. Now, if we look at a virtual machine, it's more or less the exact same thing, right? So we have this pic with the operating system that I copy-pasted 3 times. So this time with virtualization, we are running multiple operating systems on the same physical machine, right? And we do that by creating a fake version of the hardware that we call a virtual machine. And on top of this virtual machine, we are going to run an operating system. So the operating system, we call it the guest, is going to be fooled into thinking that is running on a single physical machine, while it's not. But this is how things work. Okay, we create a fake version of the hardware, and the entity that is creating this fake version of the hardware is called either an hypervisor, or you will see also the term virtual machine monitor. And in that case, the hypervisor is in total control of the hardware, and neither the application nor the guest operating system should be able to access the hardware directly for the same reason I explained before, right? So think about the cloud environment in which I am renting a virtual machine, and there is one of my competitors that is renting another virtual machine on the same physical host. I don't want my competitor to have a look at to take a peek at the memory of my virtual machine, right? To have a look at the virtual disk that I'm using. Once again, isolation is something super important. So we create fake versions of the hardware called virtual machines. So I don't have the time to explain to you how technically it is done, but it is used. Basically, we create fake software models of the hardware. And the hypervisor is in total control of the hardware and mediates the virtual machine accesses to the hardware. Okay? Yes?
Is the hypervisor also responsible for memory allocation for each of the virtual hardware segments?
Yes.
Does it manage it the same as it would manage memory allocation for processes? Can it like interchange them?
It is somehow similar. So it the same mechanism, there is no malloc for virtual machine, right? This is how you would allocate some memory in a process, but there are some similar mechanism. So basically, the hypervisor is going to allocate a fake range of physical memory, right? And give it to a virtual machine. So it is called pseudo-physical memory. And obviously, this is made on demand by the allocator. So you have, some mechanisms that are similar, some that are different. But yes, memory allocation is one of the fundamental services that both an operating system and an hypervisor are doing. An hypervisor is not very different from a small operating system. It is, actually, there was a debate saying maybe hypervisor, they are just microkernels. So they take care of scheduling of virtual CPUs, allocation of virtual fake pseudo-physical memory, and management of interrupts. Look, these three basic things. It's not really different from a microkernel. Okay. So yeah, just a bit of naming. You probably are aware of that. So the physical machine running the hypervisor, and sometimes an host operating system, it is called the host, and everything in the virtual machine is called the guest. So why is system software security important? So it's very important to note that almost every computer system today runs an operating system, right? With the exception of some small IoT embedded devices that are, not powerful enough to run an operating system, you have operating systems everywhere, right? Even on some small embedded devices, actually, a lot of them are running Linux. Look at your smartphone, right? They are all running Linux. So you have operating systems absolutely everywhere. And it is quite true for hypervisors too. So not only the entire business of cloud computing relies on virtualization and hypervisor, right? The fact that AWS, Amazon Web Services, I can buy like 100 physical servers and I can divide them into virtual machines and I can sell these virtual machines to clients. This is cloud, right? I don't want to sell one physical server to each client. I want to be able to divide them, make much more money that way, right? I buy big servers and create tons of virtual machines and run them to my clients. So without virtualization, this is impossible, right? Because each client wants to bring its own operating system. Some want Linux, some want Windows. So you need to offer, you need to have virtualization. And once again, you need to have isolation. So not only, all cloud computing would not be possible without virtualization, but virtualization is everywhere. You have virtualization in your PlayStation today, right? How do you think your PlayStation, when you put it back on, boom, the game comes back directly? It's just, it was running in a virtual machine, and the state of the virtual machine was saved on the disk of the console, right? It's super difficult to do that for a process in Linux, but it's super easy to do that for a virtual machine. Just take the entire amount of the RAM, dump it on the disk. It's much simpler. For a process, you have, okay, the address space, a lot of dependencies in the kernel, it's madness. So you have virtualization in your console. You have virtualization in your car today, right? If you have a car that is relatively recent with like an entertainment system and other things like, the things that prevent you to brake too hard so that the car doesn't slip. So these two particular tasks are very well isolated with virtualization. So you have hypervisor small hypervisors, right? But you even have them in cars. So these things are absolutely everywhere. And they are the most privileged software component in computer system, right? They have total control over the hardware. So they play really a keystone role in the security of every system, right? Say you want to develop a very secure web browser. You want to develop Chrome. It's probably a good idea to isolate each tab within its own process, right? This Chrome does that because it knows that some websites are less secure than others, and you don't want side channels between tabs, so they are isolated within their own process. This, by default, puts a lot of trust in the operating system, right? What happens if the operating system is not good enough and doesn't provide a good isolation between processes? So you see a lot of high-level security mechanisms. They completely depend on the operating system or on the hypervisor to work well, okay? So long story short, if the security of the hypervisor or the operating system is not good enough, a lot of the assumptions that we are making today about the security of higher level things is they are destroyed, right? So it's really critical, super critical, the security of hypervisor and operating system. Yep, that's exactly what I said. So what I want to focus on today is the notion of isolation. So remember, there are many aspects to security in system software. And one of the most important is the isolation of security domains. So concretely, what does that mean? A security domain is either an application. We want to isolate application from each other. It can be a virtual machine. In a virtualized scenario, we want to isolate virtual machines from each other. And it's also the privileged layer. So in operating system scenario, we want to isolate processes from each other, but we also want to isolate the kernel from processes, right? So the isolation concerns all the resources, CPU time, the memory, the disks, the network bandwidth, whatever. In this talk, I will mostly focus on memory, which is, a vast subject in itself. So what we want to avoid is an application being able to peek at the memory of another application. Remember the web browser, maybe it's subverted by an attacker. It's going to look at the memory of your password manager. You don't want that. We want to avoid, in a virtualized scenario, either an application, a guest application, or a guest operating system trying to look at the memory of another virtual machine. May it be a guest application or the guest OS kernel. We absolutely don't want this to happen. Remember the scenario in which two competing companies are renting two VMs that happen to be on the same physical machine, right? We absolutely don't want them to disturb each other. And we want to isolate the privileged layers from the non-privileged layers, right? We don't want an application to go and look at the kernel memory, right? Because the kernel memory contains everything. So passwords, whatever, if an application is able to take over the kernel and achieve something like arbitrary code execution in the kernel, it has taken over the entire machine. You can look at the memory of other applications, you can do whatever it wants. So the privileged layer needs to be isolated from application, and it is true, obviously, from the hypervisor too. We absolutely don't want, so this is called a VM escape, right? We don't want anything in the guest to be able to look at the memory or take over the hypervisor. Okay, this is isolation. And so in the rest of this first part, I want to show you what are the mechanisms that are in place to enforce that isolation. It's really basic but very concrete stuff that I'm sure you have heard about in your operating system courses. To my experience, students will be very knowledgeable about what a page table is, which, spoiler alert, is the thing that isolate applications from each other. But usually when asked concretely, how does it work? How is it implemented? Who takes care of doing the page table work, installing the page table? It becomes a bit complicated. So I'm going to try to clarify this the best I can. You'll see it's actually super simple. So first point, how do we isolate application from each other? Well, each application is given its own address space. So you know that when an application is executing some code on the CPU, it's accessing memory with load and stores operation, right? And each load and store has an address. You know, you want to write or read some data at some location in memory. And apart from the very early boot time, all the addresses used by the CPU when applications run, as well as the kernel, will be virtual addresses, right? So each process is given its own virtual address space. Each process is fooled into thinking it has access to 100% of the memory, even if it does not. On modern 64-bit systems, the address space will go from 0x0 to 0x FFF and so on. So this is 48 bits of virtual address space. Technically, you know, you don't get the entire 64. I think the newest Intel processors, they have a bit more than 50 bits, but that's, you know, 48 bits of virtual address space. It's gigantic, right? This is how many thousands of terabytes of memory. Obviously, it is very sparse. Most of it is not mapped to physical memory. So you probably know that the CPU, when virtual memory is enabled, use a mechanism called the page table that is mapping virtual addresses at the granularity of a page. So a page is 4 kilobytes, right? It's mapping virtual addresses to physical memory, okay? So it's perfectly okay for the application to access the address 5 terabytes, even if you don't have 5 terabytes of RAM. The important thing is that the address 5 terabytes virtual will be mapped to somewhere in physical memory. Okay, so completely independently of how much RAM you have on your computer, you will get access to 48 bits of virtual address space on most modern 64-bit processors. And once again, you know, this virtual address space is very large, but also very sparse. And this correspondence between virtual and physical addresses is made through the page table. So this, you know, is probably what they say in most operating system courses. Now the isolation between two applications is achieved simply by giving one page table for each application and simply making sure that they don't map the same pages. The operating system is taking care of all the mapping, right? The application don't have a say in it. And the operating system is obviously making sure that all the physical memory that is given to application 1 is not given to application 2, right? In some exceptions, they may voluntarily want to share some memory, right? Like cooperating applications, but in the case where two applications, they have nothing to do with each other, web browser, password manager, completely different page tables, okay? So what happens when you have a context switch between two applications on the CPU? Just switch the page table, install a new address space. Simple. So you see in that way, there is absolutely no way application 2 can look at any memory of application 1 because it cannot even try to address it, right? So now, how does it work concretely, right? Maybe you're familiar with this kind of schema. So this is the way the translation between virtual and physical addresses happens. So when the CPU running an application executes this instruction, so store some value, let's say 10 at address 0xdeadbeef, we are going to walk the page table. And the hardware is doing that automatically, okay? So the hardware looks at the address, deadbeef, translated in 0 and 1s, you get this thing with ABC. And the page table is simply a tree-like data structure that is composed of different pages in memory. They don't have to be contiguous, but they point to each other, okay? And the root of the page table is installed in a control register on the CPU. So CR3 on x86-32, this is very similar for 64 bits, right? It's just simpler for 32 bits. So each level of the page table, starting from the root, will be indexed by a part of the address. So you see the part A here will be used as an index into the page directory, the first level of the page table. And then in this, we find an entry with this index, and this is a pointer to another page, the page table. And the second part of the address B will point to another entry, so it will be used to index another entry in the page table into the memory. And then we use C, which is the offset within a page, to actually point to the actual data. So store this, sorry, this was 10 in French. Store 10 at 0xdeadbeef will actually hit this arrow that goes from C in the physical address. Okay, so this is done fully automatically by the hardware, right? It needs to be fast, right? Because it needs to happen at every memory access. So you don't want some software structure to work the memory and things like that. So it's done by the hardware. So the translation is made by the MMU that works automatically the page table. Obviously, you have the TLB caching this kind of thing to go even faster. Now, what's the operating system doing? So the operating system installs a new page table by writing to the control register in question. Okay, just one pointer to the root of the page table. The operating system also creates and update page tables by modifying the memory in question. If the operating system wants to, create a new mapping, it's going to modify the page table. So the operating system read and write in there. So note that all of the addresses that are in CR3, the directory entry, the table entry, and the physical address, so these are all physical addresses, right? They cannot be virtual. But the operating system has a nice view of physical memory, so it's easy for it to update and modify the page table. And last thing, when you have a context switch, as I was saying, when you have an application A that is running on the CPU and the OS wants to kick it out and install application B, just swap the value in CR3, and you have achieved the switch of page table, the switch of address space. Okay, so it's not very complicated. You have a cooperation of hardware mechanisms and software mechanisms, like the operating system setting things up to achieve this isolation of memory between two processes. Okay. All right. Now, how do we isolate the kernel from application? Right. So it's once again going to be dependent on some hardware mechanisms. So at any time, your CPU, let's say it's a single core, your CPU will be in one of the two privileged levels that you will find in most modern CPUs. So you have a mode that is generally called user mode, in which the application will execute. On x86, 32, and 64 is called ring 3. We talk about privileged rings. This is for application code. And when you run the operating system, you will be in a different mode. Generally, it's called supervisor mode or kernel mode. And on Intel processors, it is called ring 0. So one of the fundamental things to achieve this isolation between the application and the kernel is when running in user mode, the CPU cannot read, write, execute, basically cannot access memory that is marked as kernel accessible only. We don't want any application to have a peek at the kernel memory or to modify kernel memory. That would be terrible. And it's not sufficient, right? Because you have some instruction on the CPU that allows you to install a new page table. If you have the power to install a new page table, it means you can look everywhere you want in memory, right? So these are called privileged instructions. And obviously, they cannot work in user mode. So if you try to write to the control register CR3 that corresponds to installing a new page table in user mode, you'll get an exception. Okay, you will basically trap to the kernel, and the kernel will kill the application. Similar to page fault. So on x86-32, they had more than 2 rings. So we had the kernel in ring 0, the application in ring 3, and then they had ring 1 and 2 that were supposedly dedicated to running semi-privileged software, like drivers. You know, they need to access some hardware, but probably not all. Didn't work that well. And when AMD designed x86-64, just removed ring 2 and 1, but it's a legacy thing. You know, they didn't rename ring 3, so we still have ring 0 and ring 3, and we have nothing else in between. You have similar things on ARM, right? Just not the same name. Now, okay, so an application cannot read or write or execute kernel memory. So how do you request kernel services, right? You know, the application needs to ask the kernel to do some stuff, right? If you want to read, write files and things like that, you know, how do you invoke the kernel from the application? System calls, right? So you probably know a bit about system calls. So concretely, how do they work? They are not just simple function calls to the kernel. It's not possible because a function call would involve the capacity for the application to execute kernel code, which obviously we don't want to, right? So a system call, so here I have this small example in which, you know, an application runs, and then it wants to, let's say, write something in a file. So it's going to execute a write system call. So the way the system call is done is the CPU is going to interrupt itself. So the application will interrupt itself. There will be a trap to kernel mode, and the kernel is going to manage the syscall. So in user mode, to prepare for the syscall, the user code will set a syscall identifier. So you have one identifier for each syscall, read, write, open, whatever, in a register, and some parameters will be placed in some registers too, like, you know, which file you want to read and so on. Second thing, the user code will trigger an exception. So, you know, exceptions are interrupts that the processor sends to itself, right? Usually when we say interrupts, it's mostly from external hardware, like the network card is saying, hey, there is a network packet waiting for you. Exceptions are kind of internal interrupts. The processor is interrupting itself, you know, things like page fault, divide by 0, and so on. These are exceptions. And syscall is an exception. So once the application has set up the register, it's executing the syscall instruction, interrupting itself. And there is a switch on the CPU from user to kernel mode. And the CPU will jump to a predefined handler in memory that has been installed by the kernel. It's called the syscall handler. And the syscall handler will look at the register and say, oh, okay, so this is the right system call on this file. Fine, let me process that system call, right? So in supervisor mode, the kernel executes, process the system call. And then once it is done, you have an instruction that is basically returned from syscall, in which we go back to the application code. And obviously the CPU switches back to user mode, okay? So the syscall allows this safe transition, because remember, when you have the exception, you jump to a predefined handler, and it is the kernel that has said, yeah, this is the handler you should jump to when there is a syscall. And this is some safe code. And yeah, that's what I was mentioning. And that's it for non-virtualized scenario. So you see, it's not very complicated. These are some very, very basic mechanisms that make for some quite strong, but not perfect, security model for the isolation of memory. Now, real quick yeah, I should go a little bit faster. So for virtualization, it works the same. Replace application by virtual machine and replace kernel by hypervisor. So each virtual machine will be allocated a pseudo-physical address space that is completely disjoint from the pseudo-physical address space of its neighbor. Okay, same thing as a page table, but you have two levels because the VM itself has a page table, and then the hypervisor is setting up what is called an extended page table to map what the VM thinks to be physical memory to the actual physical memory. Completely separated, of course. And the equivalent of user kernel mode in virtualization is something called root mode. So I have a picture here. So the x86-64 that came with architectural support for virtualization introduced a new mode of execution, which is called root mode. And in root mode, so you have root mode for the hypervisor and the host operating system, non-root mode for the VMs. And all the rings are available in both modes. It's quite important. Because you have user applications in the in the host OS, as well as in the guest OS. So there was a lot of virtualization technique done for x86-32 that was not really virtualizable, that relied on running guest operating systems in ring 3. That was a bit tricky. But now with hardware support for virtualization, we have this root mode that allows, once again, you have some instructions that are available in root mode that are not available in non-root mode, right? You can install a normal page table in non-root mode, but you cannot install the extended page table in non-root mode. So same principle as for the application. And obviously, other privileged instructions. So think halt. So halt, shut down the machine, right? You don't want a VM to be able to shut down the entire physical machine, right? So such an instruction will trap to the hypervisor. It will emulate it, probably kill the virtual machine that is doing halt, but obviously not execute it actually on the CPU. This is containers. So what are containers? I need to relatively quick, but long story short, containers are nothing more than processes, right? There is no virtual machine with containers. Containers are a set of processes that have a reduced visibility on the system resources. You can say, okay, this container will see only 2 cores, half of my memory, and this bit of the file system. So you achieve this kind of isolation, but it's entirely done by the operating system. There is no hypervisor. There is no fake version of the hardware. It's much lighter than a real virtual machine. With a real virtual machine, you need to install an entire operating system in it for each virtual machine. It can be quite big. A container has a memory footprint of 0 for the system software. It's just a process. So, compared to a traditional virtualization stack, containers are just, processes running on top of a host operating system, but the operating system is restricting the visibility. And it all seems pretty safe, right? So we have this basic hardware mechanisms that are controlled and set up by the privileged layer, either the operating system or the hypervisor. It's simple enough to seem quite safe, but it's not. I did a vulnerability search a few days ago based on the keyword Linux kernel, 3,000 results. You can look at the results by yourself. The Xen hypervisor, which is used by AWS, at least for 100 vulnerabilities. So they have issues, right? Not every day, and not every vulnerability is very critical, but it happens from time to time. I think in 2017, there was an entire reboot of the entire Amazon Web Services platform due to a 0-day, right? So that's really bad. All the clients got service interruption because they needed to patch the hypervisor on the spot. And it's due to several things. And the thing I want to focus on is the fact that, and it's really one of the main reasons why there are so many issues. These system software, they are written in C and C++, okay? They are written in memory unsafe language. And it's mostly for performance reasons, but also for legacy reasons, right? Security was not as important in 1990 when Linus Torvalds started to develop Linux, but it's also necessary for performance. You know, if you take a memory safe language like Java, each memory access needs to be checked, right? Yeah, are you going out of bounds or things like that? This is safe, but it also takes forever, right? For each memory access, you have these checks. You have like 3 or 4 memory access per memory access. It's bad for performance. But the problem with memory unsafe language that are very fast is that it's quite easy for the programmer to make mistakes that are not only difficult to catch, but they can also be exploited. And that's what I want to focus on. So I'm going to skip the rest of these slides. They don't really matter, to go and talk about the attacks. So what would attacker want to do when they look at system software? They can do a bunch of things, which are as follows. If you abstract things a bit, they may want to leak confidential data, right? Things like passwords, cryptographic keys. If you are in a virtualized environment, you may want to leak some private data from other tenants and things like that. So reading memory, right, is a good way to leak confidential data. You may want to alter data that should not be accessible. So think about an application that somehow would be able to write in kernel memory and maybe switch the data structure in kernel memory, which says, oh, this application is executing in with root privileges, right? So that's, you know, your classical root, you know, these applications that allows you to root your Android smartphone, right? They rely on this kind of exploit. So read data, read data that you're not supposed to read, write data that you're not supposed to write, and DOS the system, right? Denial of service is to try to mess with the system, to make it crash, run out of memory, or whatever, right? So lower system availability. So these are 3 classes. You have a list here. I actually copy-pasted it from this book. So this guy is kind of one of the masters of system software security. He was a student of Andy Tannenbaum, the guy that invented Minix. So he's from Netherlands. And he wrote this book that is not very long and contains quite a bunch of interesting information. So I took some inspiration from this book in this talk. So what do we have, right, in terms of attacks against system software? Malicious extension would be like a bad kernel code that you would voluntarily inject, like, you know, an email contains a program and you click on it and it's running with administrative privilege and then you're completely screwed. So bootkit would be, you know, it would be like a virus that will install itself on the master boot record of your disk, you know, the stuff that starts to be executed right when your computer boots. So it runs even before the operating system. So it's able to obviously take control of your entire computer, but also hide itself very well. Even if you have some antivirus or things like that, you know, it's very well hidden. Memory errors, so that's the thing I will focus on in the rest of this talk. So, you know, silly programming mistakes, you know, the programmer forgot to check the bounds of memory operation. They look benign. Most of the time, the program even works. Sometimes it crashes. But actually, it can even have some very, very serious security implications. I will show you an example. Data can be leaked through uninitialized data structure. Think about the kernel that will send back a data structure to user space, but some fields are not initialized. If the user space tries to read these fields, he may see some data that comes from the kernel because these data structures has been, it's memories that have been reallocated for these new data structures, but it belonged to another data structure in the past. So you can leak some kernel addresses through this, and that's actually quite bad to break things like randomization. You just need to leak a few addresses and you're good. Concurrency bugs, say an application passes some data to the kernel checks this data before using it. Or let me check that this pointer is not pointing to nil because I don't want to crash, right? And then right after the check, somehow the user space is able to change the data before the kernel actually uses, right? So this is called a time to check to time to use. It's a race. This is a type of race condition between the privileged layer and the non-privileged layer. It can be pretty messy. Possibly you have heard about things like Meltdown and Spectre. So when applications share hardware resources, like a cache, there are some side channels. So it's some really interesting stuff. I don't really have the time to go into the details. And then you have all the DOS, like, an application trying to crash the entire system and things like that. As I said, we'll focus on memory errors. And these are one of the main issues in system software, right? So Microsoft, you can find like similar reports from Google. Chrome is, I believe, developed in C++. Most of their security issues are due to memory safety. And so these, C and C++, they are not memory safe. But so the main problem, there are multiple problems. So the first problem is that there is zero check on memory access. You are free to dereference any pointer. You are free to read and write anywhere you want in your virtual address space, right? If it's not mapped, if the virtual page that you're accessing is not mapped to a physical page, you get a crash. If it's mapped, but it doesn't actually correspond to the data that you want to read, you're going to read something else, and your program is going to continue in this bad, inconsistent state. It can have some interesting security implications. So there are spatial safety issues, bad pointer dereference, out of bounds access, out of bound buffer addressing. There are some concurrency issues. If you have two threads accessing the same data at the same time, this is actually undefined behavior. We don't really know what happens. A large part of the memory management is left to the programmer. So if you free a data structure and you use it afterwards, the compiler will not tell you, hey, there's a problem here. Things will compile, right? And then it'll get funny at runtime. Don't really know what's going to happen. It's undefined, right? Maybe it will work fine because internally the memory locator did not free and erase your data structure. Maybe it will crash. Maybe it will do something else. You have memory leaks. If you forget to free memory, you are consuming more memory than you should. What happens if you initialize a pointer on if you allocate a pointer on the stack, you int star p, and you don't initialize it, right? Do you know C? Do you know if you have a local variable? Let's say it's an int. It's not even a pointer. Will it be initialized to 0? No, it won't. It will take the value of whatever was there on the stack before. Once again, it's undefined. And all these issues can be silent, right? Oh, my program seems to work fine in the general case. Only one time upon 10 it crashes. No problem, right? So all of this may lead to very serious vulnerabilities. If you have programmed in C, probably this rings a bell to you. Launch your program and you compile, everything works fine. And then you launch the program and then you get this and you're like, what went wrong? Segmentation fault. Seg fault would be you are trying to access a page that is not mapped. So that's one of the best things that can happen to you, right? When bugs are silent, it's much worse. But this is an example of bad pointer dereference. And most of the students that are kind of beginner in C will think, oh yeah, it's just, it's okay, right? It's just a crash. But behind memory errors, there are some possibly big security problems. So I want to show you a demo. I hope, so it's a demo that I taken from my course on C. I hope you didn't have it. Otherwise, it's going to be a little bit redundant. Apologies. So it's a very simple attack that doesn't only apply to kernels or hypervisor. It applies to every program written in memory unsafe language. It's called stack smashing. So it's a very old stuff. Today, it's very difficult to achieve without explicitly disabling some countermeasures, right? Which I'm going to do. But it's simple enough that it allows me to explain to you. I searched for some exploits on the kernel, and it would take at least 2 hours for me to really go deep on it. So I prefer to be comprehensive on something simple. So what we are going to do is that we are going to exploit a very basic buffer overflow on the stack to modify the control flow of a program, to change which function it executes. And we are going to execute a function we are not supposed to execute through this buffer overflow. Once again, buffer overflow, no big deal, right? Wrong. It's some of the worst issues that you can have with overflows. So let me, first, I need to give you a bit of information about how the CPU works, how the CPU implements function calls. So the CPU doesn't know about function calls, right? The CPU just knows about machine code. The programming language knows about function calls. So the compiler that is taking your source code that contains function call and mapping it to assembly instruction, the compiler does it in a very specific way. We are going to see how it works. We look at the code for the sake of simplicity, but things work the same in a kernel hypervisor. Yes, this is user space code. So in your virtual address space, somewhere, you have something called the stack. So you have one of the registers that is pointing to the top of the stack. It's called the stack pointer. And the stack contains, for the program that is running, local variables, parameters, and things like that. So, basically, each time you call a function, the stack pointer moves a bit and allocates a new frame on the stack for the function, local variables, and parameters, and so on. So let's take this example code in which we have a function f that calls a function g, right? Before calling g with parameter x, the stack is in that state. So we have a frame for f with all its local variables, its parameter, and so on. And the call will, at execution, so if you look at the machine code, the call will be a call queue instruction on x86-64 to the address of the function g. And when the CPU encounters this instruction, when it's actually executing the g of x call, it's going to push, before allocating a frame for g, it's going to push what is called the return address on the stack, this yellow stuff here. And the return address is what is the instruction the CPU should jump on when it returns from g. Okay, so this is pushed on the stack, and then we allocate a frame for g, execute g, and when return is called, this will actually be a ret instruction in terms of machine code. What the CPU does is it pops the return address from the stack and jumps to it. Okay, simple. So you see the stack is a data structure that works really well for this thing of nested function calling, right? Allocate a frame, allocate another frame, deallocate frame. So by allocating frame, I just mean moving the stack pointer. So one thing I should precise, as you notice, with x86-64, the stack grows down. So we have high addresses on the top and low addresses on the bottom. It's quite important for what comes next. So here's the program. So let's have a look at the main function first on the right. So what I do is this program takes one argument, which is a password. So it's a program that takes a password as command line parameter. And if the password is correct, it's launching nukes, right? So the password is hard-coded line 4. Obviously, in a proper program, we will not have the password in clear in the source code, but let's assume it is for the sake of simplicity. So we assume that the input, like the person calling the program, is not necessarily a trusted person. So we use the password to protect anyone that is not authorized from launching nukes. Okay. So what I do is, so line 18 to 22 is just making sure that there is a command line parameter. Then line 24, I call preprocess input, that is just going to, manipulate the buffer that comes from the command line. So, this untrusted input. Remember, this stuff comes from the person that we don't trust, right? And then we simply compare the parameter to the password. And if the password is correct, we can launch nukes. Otherwise, we just print the fact that this is not authorized and we return. Does anyone see where is the issue in this program? So it's somewhere in a preprocess input. So you see preprocess input is calling strcpy, and it's copying in a local buffer the string. So you see the string actually comes from the command line. Yes?
You might be copying bits that you've not necessarily assigned in the local buffer, like when you're doing strcopy.
So when I'm doing strcopy, yeah, so the issue is with strcopy indeed. So look at the size of the local buffer. It is hard-coded to be 16. What happens if on the command line, I pass something bigger than 16, right? We're going to overflow local buffer, right? So this is a buffer overflow vulnerability. And you may think, oh yeah, okay, so it's going to crash, right? If you pass a string that is long enough, you're going to hit a page that is not mapped. Indeed, it's going to crash. But if you pass like something that is bigger than 16 bytes, but not too big, you get the capacity to rewrite what's on the stack. This gives you a write primitive in the address space. And what we are going to do is the following. So on the left, you just have a compressed version of the program, same program. This is the state of the stack at the time preprocess input runs, at the time where the overflow can be triggered. So local buffer is somewhere in the frame dedicated to preprocess input. And remember, the stack grows down. So the direction of the strcpy would be up, right? It's writing in memory up. So we are going to overflow local buffer, and we are going to rewrite the return address. So the goal, so let's say we are a user, we don't have the password, but we want to jump to this function, like security critical function. So we are going to overflow the buffer in the functions that we do have access to, preprocess input, and replace the value, the return value, with the address of where we want to jump, right? So we do it this way. We are going to write the address of security critical function here by overflowing the local buffer. It doesn't show very well, but we are going to overwrite all the stack from local buffer to security critical function. And then what happens when you return from preprocess input, rather than going back to main and printing unauthorized user because you don't have the password, we'll jump to security critical function. So I have prepared a demo. Hopefully it's going to work. Let's see. So I put the code online if you want to do it at home too. So I have the code here. So it's in there. If you want to reproduce it at home, there's tons of comments that I put at the beginning, because all the addresses that we are going to look at now, they will not be exactly the same on your computer, right? It's not just a simple matter of sending the same payload that I'm going to send. So, okay, I don't have that much time. I need to finish in 5 minutes, right? Yeah, I know. I don't want to take too much time. So yeah, let me go real quick over that. So we have the total description of the exploits here. So what I'm going to do is, first of all, I compile the program with a static parameter. So long story short, static is going to make that addresses are not randomized each time I run the program, which really helps to locate the address of the target we want to jump on. Okay, so if I use NM that lists the symbols in HackMe, and I search for security critical function, sorry, it should use grep. So we can see that it's this is the address. So in the address space at 0x41C8D, you have the code of the security critical function. So this is our target, right? We want to rewrite the return address with this thing. Now, with GDB, I'm going to explore a little bit the layout of the stack to know exactly how far I need to overflow the buffer from the location of the buffer. How far is the return address on the stack, right? So if I look, so I'm going to put a breakpoint on the preprocess input, the function that contains the vulnerability. I'm going to run the program with, a silly thing as a password, because, hypothetically, I don't have the password. So once I reach my breakpoint, so we are at the time of strcpy. So I need to know two things: the address of the buffer. So let me show you the slide. I need to know the address of local buffer and the address of the location of the return address. And then I just have to subtract this to know what size my payload should be, right? So the address of local buffer, I can get it this way. You see, so this is the address. Let me, actually, I'm gonna look at the address of the return value first. So I need to inspect the stack. To know the address of the return value, I know it's somewhere in the code segment. So if and I know it's somewhere in main, right? So if I look at the address of main, so this is the address of the first instruction of main. So if I look at the stack and I see something that is not too far from 41cc2, I can be pretty confident that this will be the return address, right? So let's print the stack. So that would be the stack pointer. So this is the top of the stack, right? The address contained in the stack pointer is this, and this is the value at this address. Doesn't really look like something in the code. So I'm gonna go 8 bytes, next, still not good. So remember, the stack goes down. So now I'm going up the stack, trying to look for the return address. So if I recall correctly, it's 40 bytes. So you see, look at this one, 41D0C. So it's definitely somewhere in main. It's very close to that. So this is the return address. So we know that the return address is at this address. So if I take my calculator and I compute the difference, so we are going to do hexadecimal. So this thing minus the local buffer address, what's this one? So 18 in hexadecimal, 24 in decimal. So we have 24 bytes. So my payload needs to be 24 bytes. And the last 8 bytes should be, it's a 64-bit processor, should be the address of the launching nuke function, right? So I have prepared the payload here. So let me just show first that, you know, when I call hack me with a dummy password, you just say, yeah, it's unauthorized. And I have prepared the payload here with this command. So it's, what is it? 16 bytes of nonsense. And then the last 8 bytes are the address of the security critical function. It's inverted. Remember, this is little endian, right? So you see, we have 00004001C8D, right? So this is the address of security critical function. Now, I use echo-e because I want to send bytes, not ASCII characters, right? If I just use stuff on the command line. And let's try this, launching nukes. And you see, so we have successfully hijacked the control flow just by using a kind of a silly bug that was a buffer overflow. And that's just one example of all the things we can do. So I'm going to jump to the conclusion. So you have many other types of vulnerabilities. The easy one just let you crash the system. Some give you read and write primitives. Some give you privilege escalation. Things like use after free, race conditions, return-oriented programming. So I don't really have the time, but I can definitely put the slides online if you want. So to conclude, system software security is super important. It is enforced by a set of simple hardware mechanisms that are set up and controlled by the software privilege layer, operating system, and hypervisors. The problem is that because they are written in memory unsafe languages, we have tons of small programming mistakes that may or may not lead to security vulnerabilities. There is no good solution to this problem, so we didn't have time to see the defenses. So systemic solution, like switching to a completely safe programming language or using formal verifications, they are not there yet. Nobody is going to rewrite Linux in Rust, right? It's going to take time, at least. So they need some protections. Protections are, randomizing the address space to make it hard to locate, your target, and enforcing various types of things that I didn't have time to talk about. And I think that's good to stop here. Thank you very, very much for your attention. Sorry, I took that much time.
Perfect. Thank you very much, Pierre. I think we have time for like 1 or 2 questions. Does anyone have any questions for Pierre?
I do.
You do.
Yeah. In slide 13, I had a question about there was an application at the level of the virtualization.
30 or 20?
13, 1-3.
13, 1-3.
1-3. So the user apps that's on top in ring 3 in the hypervisor and OS, what sort of applications would that be? Or is that the guest OS?
Yeah, basically it's the entire host OS. So it depends on which type of hypervisor that you use. Today, I would say KVM is becoming the most popular hypervisor, and KVM works a little bit like a VirtualBox. You have a host operating system that boots and works like any normal operating system. And then you boot something like QEMU through KVM is going to create a virtual machine that is basically a process in the host operating system. So think about this as, a host operating system with a module inside that is KVM, that is taking care of the virtualization. It needs to be in root mode to use the virtualization extension, to install, extended page tables and things like that.
Yeah, thank you very much.